Bienvenue au deuxième cours de Michel.
Thanks a lot. I think I should switch to English, isn't it?
Yeah. Sorry.
Okay. Don't fool me. Thank you. Okay. So before we start this lecture, I would like to first of all make a small remark and then summarize a little bit where we are quickly. So first of all, as you could see in the first lecture, I took for granted that you are somehow familiar with Brownian motion, elementary aspects of Brownian motion. If it's not the case, I've written down just a few pages in appendix to the lecture notes, and there is the basics that are needed basically to follow the lectures. So the beginning is quite steep, I have to say. It goes quite fast because it's 2 pages to explain probability theory, Brownian motion, compute expectations, and all that is a bit, well, it goes a bit fast, but it contains the minimum that should help you to follow the lectures. And anyway, if I'm saying something that is unclear, even concerning Brownian motion, just interrupt. That's not a problem. So now I would like to summarize the point where we are at the moment and what we ended up with in the first lecture. So we were trying to study such a controlled differential equation, and we made it mostly on the example when v of y is simply equal to y. But in fact, this time we are going to introduce a little parameter just as a bookkeeping device. But essentially, this will remain our favorite example. And we considered, first of all, what we could do if we tried to apply the first order Euler scheme. So which is just to keep the first order in the expansion of this naive expansion of this equation. And we observed that naively it seemed to lead to a convergent algorithm in case when you look at this by using this to make increments along a subdivision, you have this property that in fact the quadratic variation of x vanishes, which means that when the mesh is small, this sum here is small. Okay, so that's the first thing we established, and then we tried to move on to a second order Euler scheme by looking at one more step. And what this leads to is to make the following approximation. So there is the first term, the second one is common with before, and then there is a third term. And this third term involves something which creates trouble because we don't know exactly what we should mean by this double integral. There is nothing that tells us how this double integral should be interpreted. This is already true in one dimension, but if you go to more than one dimension, and these formulas are not very appropriate for that, but anyway, you would see that there is a real trouble. You cannot, in one dimension, there is always a naive solution. There is, just for example, I gave the Ito solution, the Ito interpretation of this integral, which is there. And what we could see by doing the computations is that heuristically, in both cases, we would have convergence if this goes to 0, which happens to be the case for Brownian motion, in fact. So we had some convergence, but nevertheless, we also observed that if we have a sequence of smooth maps that converges in an appropriate way towards x, there are many possible outcomes for this integral. We don't know exactly what we are going to get. So what I propose now is to see, okay, we don't know what this is, but this is a bit long to write down every time, and then also it's misleading. So let's replace it by a formal symbol, which I call blackboard x, and use it as a parameter and see where it leads us if we try to do the computations using this as an undefined, somehow arbitrary object, to see whether there are any constraint on it or not. Okay, so this is basically the summary for the previous lecture. Are there any questions at that point?
Just a question. When you say naive interpretation, the Ito interpretation is when x is Brownian motion?
Well, whatever. When x is Brownian motion, there is an integration theory which is done by Ito, which suggests to take this.
Yeah, this expression is valid for it's supposed to.
Well, it's
for something else you write it would have another term.
Definitely. As I say, you can. Well,
my question is whether which hypothesis you make to write these two expressions. I have the impression that for naive interpretation, you make a little assumption on x, and for the second one, you really assume that x is a Brownian motion.
No, I take this. You may like it or not, but I take this whether x is Brownian motion or not. For instance, I'm pretty sure I've not done the exercise, but I can take something which is less regular than Brownian motion, satisfies this, but is less regular than Brownian motion. I can approximate it by smooth maps, and when I look at the limit of the integrals, I get that one. There is no need that this is Brownian motion. It's just, I can adjust the convergence. I can do it for a single path if you want. I mean, I can take a single path, no probability whatever. I take a series of approximations, and in the end, when I take the limit of this object, what I get is that is something I'm pretty sure I can do.
And Michel, what then fixes the diffusion coefficients to be 1/2?
No. I agree perfectly with you. And in fact, okay, so let's make a comment. Well, you're a bit ahead, Jean-Marc. Maybe
with my coefficient. Okay.
With your coefficient, you're a little bit ahead, but exercise. Well, no, that's a good question. That's a good question. Exercise. I'm sorry. Interpret this double integral as let's say 1/2 xt minus xs squared minus, let's put a let's put plus ft minus fs, where f is alpha Hölder, alpha strictly larger than 1/3, and check it works. Heuristically, a real proof would be a bit more difficult, but check that it works. Check convergence for the example. Okay, so I'm sorry. F is supposed to be alpha Hölder, and x is supposed to satisfy this constraint. X.
And you have no constraint on f whatsoever.
Well, it's alpha Hölder.
Yeah.
Apart from that, no constraint. There's zero variation. This must be totally unreadable from. So I took this example because Brownian motion is a very important example, and I agree with you, Jeremy, that if I use this, I have Brownian motion in mind because this is the natural situation in which this is going to occur. But I can build examples, and in particular build deterministic examples for which I would get this in the end. So somehow you see, I would just have to mimic with this deterministic example. I would just have to mimic one sample of Brownian motion somehow. I don't have to define the whole probability space. So, okay. And also, I have to agree, the fact that I'm able to do this also depends on what kind of convergence I ask. What is the meaning of this little convergence? So anyway, the strategy is, let's say that this is an arbitrary object and see if really this would work for an arbitrary capital X, well, blackboard X. Okay. I don't have much room left, but maybe this is it. And in fact, this exercise will be easier to do after the third lecture. But anyway, turns out. Okay, so today we finish the motivations. So this is that part, and then we define half path. So if you really suffer too much during the lectures, you at least after having suffered today, you can leave the lectures and saying that, okay, I know what a half path is. I can stay home and have a nice way, stay in my bed. Okay, anyway. Is this the correct spelling? So the strategy will be the following. So imagine that I'm trying to solve. So I'm trying to iterate. So my recipe is to say, okay, let's take yt to be equal to ys. So let me just have a look at my notes too, so that I keep the same notations. Okay, so let's do it for the example. So we do it for the example. What I would write down, in the case of the example, all these things v of y, v prime of y are extremely simple. So if I take this, what I get is the following. What I get is that yt. Oh, okay. So anyway, let's go from time s to time u. So what I would get as an approximation would be this 1 plus, at first order, I would get lambda xu minus xs plus lambda squared, what I write down as x, and it's essentially customary to put as index for s the large variable, the small variable first and the large variable afterwards. That's purely conventional. I mean, it's that's the way it goes. Okay, so that's my approximation. And iterate. And to see what happens, there is one simple thing we can do is to say, okay, imagine that we could do it in okay, so that t is another time, and instead of going directly from time s to time u, we first go to time from s to t and then from t to u. So if we start going from time s to time u, we do s to t to u. So we apply this formula twice, and we compare. So so what we would say then is that yu should be something like ys 1 plus lambda xt minus xs plus lambda square blackboard x between s and t, and then we transport to go to time. So this is essentially yt, and then we transport yt up to time u, and then we get 1 plus lambda xu minus xt plus lambda squared blackboard x tu, and we compare. Order 0 in lambda. Lambda is just used as a bookkeeping device. I mean, it's not, we do not really assume that it's a small parameter. We could, okay, order 0 in lambda. It's essentially 1 equals 1. That's okay. That's fine. I'm comparing these two things. So what I'm going to compare is this. Okay, so at order 0, it's y equals 1. Okay. Order 1 in lambda what I get here obviously is xu minus xs, and here I get xt minus xs plus xu minus xt, which looks like a reasonable equation as well. Maybe it's not optimal in the order in which it appears is not optimal. You have to move things a little bit to have the constellation, but that looks doable. Xu minus Q. Okay. And then we look at second order 2 in lambda. And here we get something non-trivial. And the difference, somehow, if we want these two to agree, what we find is that x SU should equal x ST plus x TU plus x T minus xs xu minus x. Is this what I wrote? That looks like this. Okay, so I'm sorry. These are blackboard symbols. Okay, so we see we decided to take x as a parameter, the blackboard x, but we see that in fact, well, it's probably not an arbitrary parameter. If we want this procedure to be consistent, then we could see it as being consistent when doing refinements, or if we think about differential geometry and we think of this equation, the starting point, our starting point as some kind of a flow on the manifold. In that case, the manifold is extremely simple. It's a real line, but let's say on the manifold. Then we would expect that this flow is consistent. And this is a consistency relation for the flow, or it's a consistency relation for the sequence of approximations. So we have this little formula, and then if we look at order 3 in lambda, what we get is the following. It's only this term remain. So what we get is minus 0 would equal maybe x st x d minus xt plus xt minus xs x tu. And at order lambda 4, what we find is what is it? X st x tu. Okay.
Michel, I
Yes.
don't understand. If you consider that expansion in lambda, you should have kept into account, say, for instance, the third term in the original.
I totally agree. So that's okay.
Yeah.
So, but you see, I just put question marks there. I don't put equality signs. So these are not equality signs.
Okay.
We shall come to that. But your remark is perfectly legitimate. You're right. I should look at it. It would be unfair to imposing this relation is totally fair, because this is really something you have not missed anything. There are no missing lambda squared terms. So it's fair to impose this relation. These ones, we have to say what we want to do with them. So if I call this relation, so it will carry a name at some point. So let's give it its name immediately. This is called Chen's relation. This is Chen. So the first remark is that taking x st equals either xt minus xs squared or xt minus xx squared minus 1/2 minus s, or in fact, because of the exercise, plus ft minus fs give a valid chain relation. So the examples that you have given indeed happily satisfy this constraint. And then the way they make it with this, and then lambda cubed and lambda 4 are not satisfied, are not identities. This is related to Ricardo's remark. They are not identities. However, if let's say x has 0 free variation, and f is alpha order alpha strictly super larger than 1/3, then it's 0 equals something which is little o of t minus u. I shouldn't write this. This is in between quotes. This is lambda cubed. And 0 is even better. Let's say just like that for the lambda 4. Okay, so the what we should learn from these examples is that indeed what we get from the constraint we get from the expansion is satisfied by the examples, and moreover, for those examples, if the objects here are not too badly behaved, then these things are going to be negligible with respect to the time difference. So you see, it's as usual. I mean, if you want to solve a differential equation, the approximation you take should make an error which is small with respect to the time difference, so that when you accumulate, the total sum is going to be small with respect to the total length of the interval. So you have to do it. Okay, so this works, and you can add the following, and from this you can see the following. You can, well, it's by induction. Well, what you say, you can observe that if, okay, so x t minus xs is much less than t minus s to the 1/3, and xst in absolute value is much less than t minus s to the 2/3, which is essentially conditions that are met by the examples, then lambda 4, lambda 3, and lambda 4 are not identities. but good enough approximations. These here, 0 equal. You see, this is going to be to order something to the 1/3, 2/3 plus 1/3, so we get 1, and we say that we want it to be better than 1/3, better than 2/3, so we are done. Okay. So to conclude, we expect that if it's satisfied, as well as the chain relation that I will write down again, which is the following: x s u is equal to x s t plus, maybe I will write it down this way for one, just for once, x t minus x s x u minus x t plus the last term x tu, then the second order is naively convergent. Now, I would like to say just one word about this little relation here. So I said it was satisfied by all those examples, and it's satisfied for good reasons. One is that, in fact, if you think about it for, well, it is satisfied. And what's the meaning of this? It's essentially saying that this double integral satisfies Chern's relation. We shall give we shall see it in more detail during the formal definition of half path. But this is really related to Chern's relation, and it's, you see, the point is the following: when I write down an integral such as s less than u less than v less than t dx u dx. Well, that's a bad example. So let's change the names. Let's put u here, and let's what are good names? A and b. Well, no, these are the bounds for my interval usually. When I need names, who cares?
S1, S2.
Well, because I want to keep S, T, and U for the extremities, so R1 and R2, just to be nasty. So if I consider this such an integral, and now I imagine that I have a certain time t that I want to put in between, either it will fall before, after R2, and this is going to lead to this form. This is going to lead to a term of that. Imagine that this is this, and then I take an arbitrary time in between S and U, and I say, okay, now if this time is larger than R2, I will recover. If I impose that time R2 is smaller than this time, I get this formula. If I impose that it's in between, I get this. If I impose that it's here, I get that. Okay, so this is essentially Chern's relation in disguise. And one last thing you can say is that, of course, because of this interpretation, if my x is a limit of something which is smooth, you see that it requires very, very little for, in the end, the integral. Okay, let me write it down. It was doing it. I would like to make the following remark, that chain relation is robust in limits. If x n goes to x, even only pointwise, so in a very weak sense, and the double integral dx r1 dx r2 s r1 converges as well. You see, I'm sorry, well, if this converges, even only pointwise for S and T, well, obviously the limit is going to satisfy these relations mentioned. Okay, you really have only to have pointwise convergence, so this, which is one of the weakest kinds of convergence you can think of, to ensure that the chain relation will go to the limit. Okay, so this, my last remark is the following. So there is one last question that I would like to give an answer to before we move on to the formal definition of half path. What does it mean to be a solution of dy dyt dxt if xt is rough? And what I mean by that is that it's rough, it's not smooth, but it satisfies nevertheless those conditions. So what color should I choose for those conditions? Let's take it red. It satisfies those conditions. Well, the first thing we should do probably is to change a little bit notation. I should put a new notation, which is, so it's a pity because the blackboard was invented because it was difficult to do bold symbols on the blackboard. So but now we need more notation. So this is the new object. This is going to be a pair, which is x. We should define this, and we should probably write down dyt equals d of yt. People don't do it usually because everyone knows what he's talking about, but it would probably be more honest to do it that way. So we should show in the notation what we have in mind. So this should be d. We should use this notation in the equation, and the meaning is yt minus ys minus xs, I'm sorry, d of ys xt minus xs minus, well, I'm just st, this quantity here would be a little o of t minus s. So this is saying that y solves this equation. We will write it that way. X then is a pair made of a standard path and this strange object here satisfying chance relation. And then solving it means that when I take this difference, I get something which is small with respect to t minus s. And you can check that this works. X is smooth. And at first order, well, what we understand, we're at first order Euler. And I don't know how to I don't know how to formulate it better than that. I mean, of course, when we think we are used to see differential equations. So when we see, you see, when we see dy over dt is v of y, well, we say okay, we have this derivative, and we want it to be equal to this v. We don't say that, well, but in fact, this turns out to be equivalent to the fact that yt minus ys minus v of ys t minus s is little o of t minus s. These two things are exactly equivalent. Well, I'm not saying precisely what I mean by this little o uniform or not uniform or whatever, but this is this theorem.
If X is smooth,
Yes.
you have no choice. You have to take the naive usual interpretation. No?
Well,
Or for the blackboard X, can you now really do anything?
yes,
Even if X is smooth?
yes. That's the example we shall see. Yes, definitely. Not only can we, but we are forced to. Yes.
I have the question. In the hidden blackboard, you said, okay, chain relation is compatible with the integral in the three terms you can really interpret it. But can we use this thing to, if X is smooth, can we just use this concatenation relation to show that it has a naive value? Is there, so are we dropping some hypothesis? Is it that because we make some hypothesis?
Well, yes, because the Ito procedure satisfies chain relation as well. I mean,
yeah. Okay, I understand that. So this relation is not enough to fix it, but by an extra assumption like maybe that's the behavior of ST when.
Oh yeah, definitely. But well, you see, no, I'm afraid not. No, we'll see in the example if you're satisfied by. Well, if the example convinces you, if not, we'll discuss again. I think the example will illustrate your point. So let's try to get to it. So this ends the motivation part, and we turn now to a real definition of reference. And this will contain two parts. The first one is combinatorics. The second one is regularity. And essentially, what I'm going to do is just to copy, just slightly more generally, the chain relation to the combinatorics, and the regularity is going to be given by what is one. I will be slightly formal. There is a question. No, AB be an interval. R. And imagine that E is a vector space. and alpha belongs to 1/3. Let me yeah. I guess this is the way to put it. So its definition, def, a graph path order alpha on AB with values in E is a pair. I denoted, I keep the notation I had before, X, and blackboard X. Well, it's, of course, it's a stupid remark, but if you look at LaTeX, when you ask for boldface X, the bold is in this direction, but when you ask for blackboard, it's in this direction. That's the way it is. So I adopt the LaTeX convention. So it's a pair where X will be the path X goes from AB well to the tensor product E tensor E and chain relation. So the generalization I'm doing with respect to what we did before is that I concentrated for simplicity to avoid indices or whatever, to concentrate on the one-dimensional setting. And I've tried to write down the formula so that they could be copied nevertheless easily. But chain relation is just that X S U is equal to X U plus X T minus S. And now we have to put down the tensor product X U minus S. So this is a rough path. It's a standard path, so it's a function of one variable. It's a function of two variables, and they satisfy a consistency relation. That's a combinatorial. Well, so and just to be sure, we shall impose some regularity. So I call it a combinatorial rough path. I'm missing some essential information, as we shall soon see. I'm missing something essential. I have to impose some regularity conditions. And in fact, without these regularity conditions, you may wonder why we are asking that alpha. Well, alpha doesn't appear in the definition for the time being. So let's remove it from the definition. I'm sorry. Let's just remove it. It's combinatorial.
Is two in some sense because you. Yeah, the order alpha. So.
It doesn't have an order, and it's two components. Well, with two components. Yes. Thank you, Larry. That's a valuable thing. Indeed, we could imagine doing things when we go to higher orders, and we shall. I shall give.
Michel, do you assume that the vector space is finite dimensional?
No, I don't. Okay. I don't, and in fact, well, it's said that, well, in the books, they say that in fact rough path is unusually friendly with infinite dimensional spaces, so that basically anything can be done in infinite dimensions without much trouble. So I don't assume this. Well, in all our applications, it will be 1 or 2 dimensional. But that's just for your for the generality. Rough paths are very friendly with infinite dimensional spaces.
No, before in X, the blackboard X, you were assuming that the more or less that order.
No, well, yes, okay, that's a good point. I don't do that. And this is for every, you're right, I should be precise, every S, U, and AB. They don't have to be ordered. But in fact, the argument I gave for the commutativity of the flow of the differential equation, for the chain relation, yes, I gave this this argument that it should hold by putting t between s and u. But for instance, for the closure of the flow, you could nothing imposes you to go forward in time all the time. You could decide to go backward a little bit and then jump to you go backward in time from s to t and then jump from t to u. This should also close the flow.
Okay.
So
I was just wondering whether the axioms you give imply something like x of ss is 0 or there is symmetric or anti-symmetric when you.
Indeed, well, okay, so that's why it's not anti-symmetric. We are going to give a few properties now. Yes. Pop. Oh, that's not what I want. Oh, yes, there we go. So what did I want? So yes.
Sorry, Michel,
Yes.
question that.
Yes.
Is there any reason why we're open?
Oh, no. But usually you always face trouble when you try to solve differential equations, even ordinary differential equations. Yeah, infinite time may cause trouble. And in fact, when I was discussing what I was doing was very formal. When you talk about convergence, usually you can get it only for a finite time. But this would perfectly hold. The point is that then when I would give the regularity conditions, I would have to say that the functions I'm looking at are not Hölder, but only locally Hölder and all that. But this is just technical. Does that answer the question? You have 10 seconds to react. So the first thing I would like to give some properties. And the first one is what I call gauge freedom. If x is a graph path and f goes from f is this time I call it a path with target the tensor product E tensor E, then x prime, where x prime st is x st plus ft minus fs is also a rough path. I'm sorry to be so bad with the black. Also is also so I call this gauge freedom. Once you have one solution to the chain relations, if you add ft minus fs, you're done. You get another rough path. And in fact, the converse is true. Exercise for you. This is a very simple one. The answer is in the notes, but exercise. X x prime, the same x are rough path, then x prime minus x, let's do it that way, satisfies Chern's relation. This is trivial. So can be written as an F. You see, the point is that obviously, apart from this little thing here, this is just Chern's relation. To think of it as an integral somehow. And when you take the difference, of course, this drops. And so this is trivial. Well, this is, I'm sorry, trivial. Okay. In fact, I already know a few coins to Jeremy, and I will add a few more because I'm. No, we are not in the group de travail, but anyway. It's exercise. Thanks. Okay. Well, I will do my duty. Okay. So, in particular, this is a consequence. In 1D, xst equals 1/2 x3 minus xs squared plus
Michel, you have a question.
s. I'm sorry?
You have a question.
Okay, I just finished. In one dimension, you can write down the most general solution to the Chern equation easily.
Does it mean that from a rough path it is
Yes,
not?
definitely.
Yes, but
Definitely.
okay, I missed the.
No, it's definitely. Okay, so that's it. And then I'm sorry, I will have to look at my notes closely because this is something I always. Yes.
But that you say in 1D, it means 1D time or 1D?
1D. Because in 1D, this double integral always can be interpreted as this. It's trivial. It fulfills well. This satisfies well. This satisfies Chern relation in 1D if the space is one-dimensional. This is what we did in the exercise with the little differential equation we had. And well, this is, you see, this is the naive interpretation. This is the naive dx u dxv s2t. It satisfies the Chern relations, and then we add this. And so I have to look at my notes because this is something I always have a tendency to mess up. So it's just to explain the name rough path. You see, you could say that we are slightly in a poor position because we define the rough path as something which is not a path. I mean, we have x, so and what I want to say is that, okay, I will have a look at the notes to get the explicit construction is just the following. Using Chern's relation, X ST can be reconstructed from X AT and X. So you only have, you can fix S to be the beginning of the interval, only give this, and then using chain relation, you can recover this full one. Well, this is pretty obvious. You just look at chain relation and do what you have to do. You can have a look at the notes, but you can reconstruct. So if I give myself X AT and X A dot and X dot from AB to E, answer E, or E for the second one. Then I recover X. Can be retrieved. So from that viewpoint, this half path is a contrived way to define a path. And in fact, there is some kind of reciprocal. Any combinatorial, there was a question.
At the beginning, you said that X is a path.
Yes.
What is a path of continuous function?
No, not even. For the combinatorics, who cares? Well, in 1 second, I will give regularity conditions, then it will be better than continuous. But for this definition, there is no reason to make it. It's just a function. Okay, good point. Usually in books, a path is a continuous function. So I can assume it's continuous. It doesn't matter because in 1 second, I will impose more than continuity. So, but just for the combinatorics, you don't have to have any regular. Any combinatorian graph, I'm sorry, any path X AB to E can be lifted. This is the usual term to a combinatorial graph. And again, yes.
So you say you can reconstruct from X. Did you say that I can take any X of A something and can take any?
Well, that's what I'm going to say here. But what I was saying there is that if I'm given a half path, so the two components, I can concentrate only on XA and as a function of the second variable and reconstruct the full X from it. Now I'm going to say the contrary, which is, I think, well, the reciprocal, which I think is what you mean, is that in fact, if I give myself two paths, one from one going to E and the other one from E to E tensor E, I'm sorry, then I can use it to construct a half path. So that's okay. So reciprocal.
Michel, now I'm confused what is a path because you started no hypothesis on path, and now which path is that one? Is path continuous or non-continuous?
This okay. So I will.
You have to decide what is path in the whole lecture.
We'll see that. The point is that. Okay. You know, it's. No, there is a functor in this. So if you want really to be pedantic, there is a functor. If I start with making no constraints on paths, then I make no constraints on paths there. If I say that my paths are continuous, then I will give a continuous lifting.
I appreciate the remark.
It's functorial. I mean, it's just, you know, there's a forgetful functor, you can forget continuity. Well, anyway, I'm sorry. Sorry for the real mathematicians who are listening to me. I'm just joking. So let's say it in detail, nevertheless. So the point is the following. So I imagine that I have X first component, which goes from AB to E, X second component, which goes from AB to E tensor E. Is that correct? Yes. And then I define XS. The definition is X1S and XST. Again, by definition is, let me just say, the definition is not complicated, but I always make it too complicated. I'm sorry for that because I'm obliged to read my notes. Minus X minus XC 1 tensor X1 T minus X1 S, and C is an arbitrary point. So I fix these two things, and I fix C in AB. And I give this definition, then you can check that XX is a combinatorial And just to please Ricardo, I just make the observation that if I put no assumption of regularity on the x's, that of course, well, I'm happy. But if I put some regularity, if I decide that x and x1 and x2 are continuous paths, then, well, obviously this formula also has the continuity property.
You're starting with a path from AB to E.
Yes.
X1 is the same.
Yes.
What is X2? How do you define X2?
X2 is whatever. I take whatever, and then I construct a half path with it. You see,
Take whatever.
I take x1 and x2, whatever I want, and I construct an x with this, and I get a half.
Sorry, could you double check the tensor part of in the definition? The indices. I don't S minus what? The x minus.
I'm sorry. What is so? I think yes. I think this is correct.
What is C?
C is any point in AB.
Ah, okay.
I was just saying that when you said S equal A in your formula for Blackboard, the point is that it's supposed to give X2. X2 is your candidate for X of A something.
So X2 is completely arbitrary.
Yes, X2 is completely arbitrary. And I think the subscripts are correct. Okay, so from the combinatorial point of view, there is not much in half path. It's essentially a dull world. The world of combinatorial half path is dull.
I guess you missed the usual tensor product.
Where?
X2.
X2 is takes. Oh, I'm sorry. Is that what you mean? Yes, I agree.
Just can you stop? I would like to say that the students in the virtual room can switch on their microphone and ask any question because we will hear you. So there is no problem.
So,
Yeah, now, yeah.
I can just answer your question. In fact, we will give a kind of answer when I define regularity conditions. Indeed, maybe I wouldn't rephrase things exactly as in your question as rescaling S and T, because you see, essentially, if you think about it, this is essentially invariant under reparameterizations. All the conditions we gave are invariant under reparameterizations. So there is no, but nevertheless, once we add regularity conditions, some kind of scaling will emerge among the different components of the half path.
Michel, sorry again, I'm very dumb. Why don't you take X2 to be 0?
Yes, why not? Yes.
Then it gives you a construction only with the data. with X.
Yes, if you want, yes. But you see,
Minimal error.
it's not surprising because
C'est la
you
gauche.
know the gauge invariance
C'est la gauche.
you can remove. Yes, I totally
You
agree.
don't need X2 at all.
I don't need X2 at all. I agree. But
You
this
make
is,
it better.
but this, I'm sorry, this is the most, somehow the point is that
But you
this is
gauge.
the most general rough pass you can make.
Just gauging something.
But you, this is the gauge. That, totally correct. Yes.
Use the translation lines, the eight is in the X2 to 0. Because here it's the construction is using A as the original time.
Maybe speak a little.
So, see you in a few minutes.
You mean coffee break?
Yes, isn't it?
As you want. Okay.
Well, yes, I think so.
CO2.
About regularity, so I will remove the qualification of combinatorial, and I will give really what a rough path is. And from now on, when I will talk about a rough path, it will be a real rough path. So now I take alpha, which is in the interval not 1/2, and if I'm correct, this is what I want. And so a rough path is a combinatorial rough path and so if to be precise, because Jeremy is going to ask me to be precise, a two-component rough path, and here is of order alpha, combinatorial rough path, so it's my pair X, blackboard X, such that X is alpha holder AB. But this means that if I take the supremum over S that's equal to T in AB XT minus XS. Oh, I'm sorry. Yes. Alpha is there, and also I have to assume that E. I have to make some assumption. E comes with a norm. It's so-called Banach space. So it's the usual assumption. You can forget about it. You can think about E being finite dimensional. We don't really care. But this is a Banach. There is a norm anyway. So minus S. The alpha is strictly less than infinity. X is such that on this side is the same. The sup is not equal to T. ST norm divided by T minus S to the 2 alpha is infinity. And of course, I'm cheating. So here I should add a little subscript. There is a norm on E. And of course, here, this is the same norm. And here it should be a norm on E, tensor E. And so this is a special gift for Chiron, in fact. You will understand why in a second. Usually in these lectures, E is finite dimensional. And then any norm on E and E times E is okay. They are all equivalent, and so this gives the same. You can change the norm here, the norm there. It's not going to change what you mean by your alpha. The objects are the same. It will just change the constant, but apart from that, infinite dimensions. Now, in infinite dimensions, in fact, if you have, it's just a remark. It's just really for the fun. Given, it's a theorem that in fact there are 14 nice norms on eta tensor E. And this 14 is the first mathematical exploit of Grothendieck, in fact, the computation of this 14. So that's why it was a good for Kiran. Okay, but only one, the projective norm, is half-pass friendly. And it's the one that allows you to linearize bilinear forms, by the way. Anyway, so that was for. You can forget about this completely. It's just because I know that Kiran loves tensor products and Grothendieck, so if you put the two together, of course.
The only one.
Have a simple definition.
It's the projective one, so it does a supremum of something. It's well, okay. So I'm going to say maybe someone can correct me. It's some kind of generalization. There are two extreme ones, which are the injective and the projective norm, and somehow they are related to the difference between L1 and L infinity. Naively. Okay, so please correct me if I'm saying something stupid. But that's. So you see, if you think this is all related to convexity questions, and then if you draw the unit ball for L1 and for L infinity, you see that they are imbricated in different ways. One is a cube, and the other one is also a cube, but it's in square. Okay. So I think there is some kind of. But it. Yes.
Sorry. Yeah, just to be pedantic.
Yes.
E tensor E is not the algebraic tensor product.
No,
you complete.
No, and I agree. Yes, that's why I said it's a Banach space. And, it's not the algebraic tensor.
No, you said that E is Banach space, but you didn't say that E
yes,
times E is a Banach space.
Yes, so there are essentially 40 different ways to endow the tensor product with suitable completion as a. Well,
now I am happy.
I'm sorry?
I'm happy.
Oh, you're happy. That's perfect. Yeah, okay. So I didn't want to spend too much time on that, first of all, because I don't understand it at all. It's just, I'm just like a kind of drum here. You make the noise, but I'm not the musician. So it was just for the fun of it. So anyway, I will make a few remarks, and then we can at last go to the example. So, first of all, why the restriction in alpha, and in fact, one of the restrictions is easy. Alpha larger than 1/3 implies, for instance, that X has vanishing free variation. This is a bit. You see, this condition is not reparametrization invariant. Nevertheless, if alpha is larger than 1/3, then X has vanishing free variation. So we are in the good position for the exercises we made the previous times, and also X is okay, and naively, so this ensures you have closure of the flow. Of RAF. Differential equations. Okay, so that's it, and alpha at less than 1/2. If alpha strictly larger than 1/2, x has vanishing two variation, in fact. And first order Euler is enough. Moreover, there is only one possible x, because you see, because two different, the difference of two candidates would be 2 alpha Euler with alpha strictly larger than 1/2, and so a function which is more than 1 Euler is constant. So, so there is only one possible x, and just as a teaser, x equals xst equals the Young integral that we shall define. If you look in, I'm sorry, okay, let's write things in intrinsic way. This is going to be integral from x t x u transpose dx. So we shall define a notion of integral, which is rather naive, in fact, and the only possible blackboard x is going to be given by this integral. So there is, if we want things to work nicely, we have to make this assumption. If we relax this assumption, then we would have to add more components to get it, because we would have to go to a higher order Euler scheme. We would have to add more components, which maybe I will say a few words about that at some point. But okay, but if we want to be in the setting that we developed in the motivations, we have to put this restriction. We have two component graph path. Going to alpha below 1/3 would require to add more components. And then for if alpha is larger than 1/2, we do not gain anything. There is only one possibility. Nothing changes. Doing the first or the second order Euler scheme is not going to change anything, because there is only one candidate for capital X. Okay, and then the last remark I want to make about these analytic conditions. Beware. The topological
sorry to stop you. You have a question.
Yes.
What does x is okay mean?
Oh, what I mean by this is that if x satisfies this 2 alpha regularity condition, then if we use this second order Euler scheme to make the to compute solutions of graph differential equations, then in fact the flow is going to close. In the language we used before, it means that the lambda cubed and lambda 4 terms will make a negligible contribution. Yes, I agree with you. Then it was just a shortcut, which is not too good. Okay. I hope this is yes. Okay, so that's exactly what I was going to say. So as we saw in the previous part of the lecture, there is a tautological way to lift a path to a half path. And what I wanted to say is exactly an answer to your question. The tautological construction of a lifting fails to give more than a combinatorial. Half path. And for instance, if X is alpha Hölder, then if you look at XT minus XC, if someone has notes, I'm happy to get XT minus XS. So this is a combinatorial candidate. Combinatorics, okay. Is okay, but only alpha over 2, not alpha or okay, because here is C, it's not T. C is any member of AB. I could take A if you want. No, that doesn't matter. Changing the.
You mean tautological construction is the previous one?
Yes.
You get x1 and x2. And
Yes,
you say
exactly.
x2 0.
Yes, exactly. This is yeah. So if you do that, you get only something which is which satisfies this condition here with alpha over 2. So you only have alpha here, but not 2 alpha. So this tautological construction doesn't work. And there is the good news. There is a difficult theorem saying that lifting is quote unquote always possible. But it's you see this little formula here. I was able to find it for myself, so it's not very deep. However, the real proof that you can. So this is a candidate. It doesn't work usually, and the idea is that you should look now for the second component to cure the disease of that one, and it's doable, but it's not trivial. And well, it's a few pages, and well. For those who know it, the argument is somehow related to the argument for the regularity of path in the Kolmogorov sense of theorem. But okay, for those who know it, it's a bit similar in spirit, the proof. What did I make wrong? Okay, so now we can. Does this answer your question? Maybe. And there's another question.
I'm not sure you understood. You take X alpha Hölder and the blackboard X, we want it to be 2 alpha, right?
Well, have exponent 2 alpha. It's not really an Hölder condition, but okay. Well, this condition with 2 alpha, yes.
Yeah, because you wrote combinatoric only alpha over 2, not alpha for X.
It means
Yes,
alpha
which means that in fact this X here is going to satisfy the right condition, not with what we want with 2 alpha, but only with alpha.
Okay.
Does that?
Yeah. Okay.
So it fails. That this is not going to. So X is not an alpha half path. In general. Of course, you can find example when it is, but generally, it's not going to be an alpha half path.
Just what you wrote before, your tautological construction, the first index was XS and not XT.
Maybe. Well, then the only thing I can say is that you could just check that well, what is the right one? Yeah, okay. You're right, this was XS. Well, and I hope the notes were correct.
So the statement is that X blackboard satisfy that condition with alpha, not 2 alpha. But instead of writing alpha over 2, not
well,
alpha.
I have to replace alpha by, I take this and I replace alpha by alpha over 2. Yeah, but if you want, yeah.
Okay, I understand. We have a different logic.
I'm trying to, it's terrible. I mean, I'm trying to spare a few seconds to keep time for the example. And of course, every time I try to spare a few seconds,
you lose a
minute. Okay, so we can go to the example now. Okay, so, but maybe it's worth summarizing. So there is a combinatorial condition, which is the chain relation. There are some analytical conditions, and they can essentially always be fulfilled. And okay, so just let's make a remark. So this is a theorem of existence that giving X, you can lift it with a blackboard X. However, this is definitely not the way people do usually. Usually, they have a natural way to choose blackboard X, for instance, because things come from some kind of limit, or for any other reason, or because there is another integration theory that gives you an answer for that. For instance, this X here, for Brownian motion, we have good reasons to take, at least in many circumstances, the Ito formula for it, which is given by a different integration theorem. It's not half-path integration. So the point is the following. Half-path theory gives an abstract construction of a half path from a path, but this is not, it's useful to have this existence theorem, but usually you rely on something totally different to decide what is going to be your blackboard X. And I will give some examples. Okay, so now we can go to the example, which is a new chapter, but it's a short one. And I hope it will be at the beginning. It's a minimal example of half path.
Michel.
Yes. Another question.
Yeah, but cannot.
Yes, definitely. You're right.
If the scalar are not a vector, then lift.
Yes, to half path is trivial. Yes, that's totally correct. Problems only occur when you have more than 2 components, at least 2 components. And in fact, you will see exactly why in the examples I'm going to give. So this is the 3rd chapter, a minimal example. Chapter 3. And so what we are going to do in this chapter is first to give this example and then use this half path to solve a half differential equation and see what it leads to. So the example is easy. Define. So let me just fix my notations just to be sure that I put things in exponent or in then epsilon is defined to go, and this time you see, this time I take an infinite interval, it's not important, but okay. And the values are in C, that's why I call it Z, and I'm sorry, this is 0 infinity, and at time t associate square root of epsilon e to the I t divided by epsilon. So this is a family of paths. Okay. And so you see, it's just you are going to adjust the radius, but you are just looking at something that is wrapping around the circle. And when epsilon is so imagine that epsilon is strictly larger than 0, and then when epsilon gets smaller, the radius of the circle gets smaller, but you just wrap faster and faster around the circle. when epsilon gets small, okay? And what I'm trying to show you is that, in fact, this here has a non-trivial half part limit when epsilon goes to 0. Okay, so let me write down. So whenever I need it, I will say x epsilon plus y epsilon is equal to z epsilon. And then sometimes, just to avoid thinking of it as an exponent, maybe I should. So this is a definition. This defines x and y. Okay. So now we can. It's easy to compute integrals, and of course, if you make the computation, for instance, if you compute x epsilon d x epsilon from, let's say, s to t, well, this is easy because this is a total differential. Everything is smooth. So what you are going to find is just epsilon over 2 and cos squared t over epsilon minus cos squared s over epsilon. I hope I didn't make any algebraic mistake, but it looks okay. And you see this goes gently to 0. There are many ways you can see it's going to 0. It's uniform. It's even better than that. But anyway. Okay, and same for x. Idem for y. Now, on the other hand, if you start looking at the integral of x epsilon dy epsilon, of course, it's not very deep. You see, there is already a difficulty. Here, I didn't even have to think. I just had to say, okay, this is x squared over 2 taken between the two limits. Here, I have to compute a real integral, so of course, it takes me an hour. But in the end, the result is not too complicated. And what you find is that this is 1/2 t minus s, if I read it correctly, plus epsilon over 4 sine 2t divided by epsilon minus sine 2s divided by epsilon. And analog for well, in fact, I write it. Let's write it down because it's instructive somehow. If you do the computation, it's minus 1/2 t minus s plus epsilon over 4, and the same here. And without surprise, if you look now at the sum s to t of x epsilon dy epsilon plus y epsilon dx epsilon, this is a total differential, and you recognize it immediately. It's a trivial total differential, and this is just going to be epsilon over 2 sine 2t epsilon minus sine 2s epsilon. And so what is interesting is the area, which is 1/2. Okay, I will make it some. So I just have to be sure x dy epsilon. And this is going to be, if I'm not mistaken, it's just going to be. So I'm summing, and I have, so it's going to be 1/2 minus x. So you see, all these guys here go gently to 0. But this one doesn't. Okay, so first of all, just to start with, this guy here is going to 0 very gently. When epsilon goes to 0 uniformly, it's going to shrink to a point. However, the scaling was chosen in such a way that all the trivial tautological integrals, the total differentials, they go gently to 0. However, there is a finite area. Okay? And so, well, we have our first example, well, simple but non-trivial example of a rough path. So this is going to be the 0 path, but if you allow me to write down the integrals as z epsilon and keep some kind of complex notation, then in fact it's going to converge. It's going to converge in the following way, just easy. This is going to convert to something which is ZST equals T minus S 0 minus I 0. Epsilon goes to 0. And of course, I should explain a little bit my notation. So I define Z epsilon ST to be the integral from S to T of the matrix guy, which is, so I take Z U minus ZS, we all have epsilon EZ U epsilon, and then the other component is Z epsilon U minus Z epsilon S D Z bar epsilon U. I should put all the little things here. And here I have the complex conjugate, so it's going to be Z bar U epsilon minus Z bar S epsilon D Z U epsilon, and the last one is going to be the trivial, again the trivial one. Or epsilon minus Z bar S epsilon T Z bar U epsilon. This is a little, you see, this one had 2 components, so this one has to have 4. So this is what it has in this representation. C is the same as R2. So C tensor C is the same as R4, which I identify with 2 by 2 matrices.
And the definition is such that if you write in components, is the usual one for each component?
Well,
or there is something more? I mean, if I rewrite the...
Well, if you expand, you will know it will be linear combinations of the usual ones.
No, but if I write Z epsilon E, Z blackboard epsilon as X blackboard epsilon plus Y blackboard epsilon, and I take the imaginary part and real part, I get the usual definition for X and blackboard X and blackboard. It's tedious to say blackboard. Okay.
At least maybe modulo 3, well, you see, you choose some isomorphisms to do that, so there might be some factors of 2 somewhere or whatever.
Okay.
These are details. So this is my object. And so you see, here is an example of a rough path. So you start with something which is smooth. The first component goes to 0, but the second component doesn't go to 0. So we managed to construct things in such a way that even if we are looking at the approximation of using only smooth things, the limit is not the smooth one. And this, of course, you could say, okay, this guy here is very smooth, this guy here is very smooth. We call this a rough path. And the point is that each of them independently is a very nice guy. But if you think of getting this integral from this path, it's not the case. I mean, you have to do something well. In fact, by the way, this morning I was wondering if there could be some way to rephrase all this in terms of infinitesimal, you know, this non-standard calculus, that you could keep track of what happens. You take this here with epsilon supposed to be an infinitely small real in this infinitesimal version of the reals. I mean, like Euler would have done, and maybe then there is a way to rephrase this in a different way using these infinitesimals. I don't know. But this is really the image you should have, that if you look at large scales, you only see z equals to 0, but if you really zoom in, you see that in fact, locally, it continues rotating tremendously, so that in fact, the area it remains finite. So this is the big...
Alpha, là, il vaut combien juste? Alpha.
Oh, okay, so we are... Okay, good question, Vincent. That's what I'm going to come here. So, first of all, you see that you can go up to alpha equals 1/2 for this one. If I look at this definition here, I see that 1/2 is okay. So, okay, and so I will say something about. So this is just a computation, but there is something. In fact, this is something that can be predicted from abstract arguments. So let me mention the following. Let me mention the lemma. And I will state it only for Hölder function, but it has an extension for Rashba.
Michel, you have a question, just to...
Yes. Okay.
You will have a question. You will have more questions.
Have you switched on the sound? Have you switched on the sound, because there are questions and we don't seem to hear them.
No, Sanjay is muted.
Sanjay, you're muted.
Non, c'est vrai qu'il y a quelqu'un qui parle et on l'entend pas.
Où ça?
Regarde, il y a quelqu'un qui parle, mais ici on n'a pas de son sur cette. Ah, ouais, peut-être. Bien, oui, on a un micro qui marche, mais on n'a pas de.
Oh, okay, and Sanjay can hear the questions, but I don't know.
Le son passe. Oui, on a entendu. Quand on a éteint le micro, on l'a rallumé.
No, but it's
a very late
yes.
lunch today because
No.
you're wasting time.
I don't understand the problem.
Okay.
Yes.
Yes, yeah, it's not. I did nothing.
Il est nothing.
We can hear you. So what is the question? Yeah. Yes. So this. Okay. If you allow me, I will answer the question. Okay. No. Let's answer it immediately. Okay. No. You're. In fact, to be honest, this was something I should have said at the end of the previous chapter. But you see, the point is the following. Okay. So you see, when I say that I ask something which I call X alpha, which by definition is this supremum S not equal to T in AB xt minus xs norm in the space E divided by T minus S to be alpha to be strictly less than infinity. So this gives me a size for this number here gives me a size for X. And so for instance, I can from this deduce the size of X minus Y in alpha, okay? And then I say that X and Y are, this is going to define, so this defines the space of Holder functions, and then this defines also a distance on this space. And then I say that X and Y are close if this guy is small. And idem, and you can do the same for X.
You wrote the soup, but you didn't write that it was your norm in the previous chapter.
Sure, no, I agree.
The detail is that you don't care about constants. X is a constant. You have a small norm. You have non-zero. So.
Yes. Okay. So I'm sorry. So same for X. So there. Okay. That's correct. So same for X. And so now, okay. So you have X belongs to the direct sum of E plus E tensor E. It's the subspace, quadratic subspace given by two relations. So rough path are, let's say it's a quadric, if you want to say, subspace, not linear. E plus E tensor E, and X is close to Y if let's say XA minus XYA norm E is small as well as the norm of X minus Y alpha and norm of capital X minus capital Y. Sorry, this is Y alpha. So this is a way to put a topology on these spaces. You say that they are close if these objects here are small, these differences, and also just to fix the constants, you also add that the initial guy should be small. 2 alpha. Well, this is, in fact, if I did it correctly, I think the subscript I put, it's the definition of this guy involves the division by t to the minus s to the 2 alpha, but I denote it by alpha as an index. This is just a notation. I could 2 alpha would be okay as well. But, I think it's yes. No. No. If you want to have a norm, okay. So that's related to the other question about scaling. It's true that from the scaling point of view, the square root. Okay. Is natural to compare norm x alpha. However, this guy is bad because it doesn't satisfy the triangle inequality for distances. You see, because of the square root, it doesn't qualify. So the one I have in mind is that I put, so I could decide that my norm is any, if I take positive numbers, P1 XA minus YA. So let me just put one. So P1 XA E plus P2 X alpha plus P3 X alpha, P1, P2, P3 strictly larger than 0. This would give me a way to define a distance. And in fact, changing P1, P2, P3 would just give equivalent distances. So it doesn't matter. So that's why you forced me to introduce these guys, but that's why I chose this informal. The precise values of P1, P2, P3, of course, they are important to compute what I would call the distance, but however, they do not change the space of rough path, they do not change the topology, whatever. They are irrelevant. You're welcome. Okay, so now we can go back for our little results. We're of course not done what I wanted to do today, but who cares? That's not so important. So let x n be. So it has an extension to half path. I state it only for the older case. It's a sequence of path. It will be to E with a norm such that x n converges to x pointwise. So really the weakest kind of convergence you can imagine. And for some beta in 0, 1, so n of norm x beta is strictly less than infinity. So there is a common constant. I take all the possible older norms of these guys, and I imagine that it is bounded by something. Then yes, thank you. Thank you. Then xn converges to x uniformly on AB. X is beta older. And xn converges to x in norm x, norm alpha, or alpha in 0 beta. So let me just rephrase it. So you have this sequence of paths, and you imagine that they converge pointwise and that their beta Hölder norm is bounded. Then you have uniform convergence. The limit is beta Hölder. Well, that one is easy. If you have simple convergence and you have this condition here, then this is going to say that the value for x is going to be less than the sum of these values, so it's going to be beta Hölder gently. And then what is more interesting is that the convergence also is going to be in the Hölder topology for every alpha strictly less than beta. So that's the theorem. I will not prove it. The proof will be in the notes, but maybe not in what you will get next week in your mailbox. But let me just take a few minutes to illustrate how this theorem is at work in our simple example, because it's instructive and I don't have the time to anyway to do much more today. So this means there's the cliffhanger that you will have the end. The most interesting part of the example is for the next lecture. Now we have Z epsilon, and now look. Let's imagine that I look at Z epsilon t minus Z epsilon s. So again, I advise you to. So I use this simply for the module for the complex number. I advise you to try to do also the proof. It's easy. I mean, it's maybe it will be even in the notes. Again, so this is an extension to rough path for a theorem for convergence of rough path. This is called the interpolation lemma, in fact, in the literature. So I do it again only for the first component, but things go the same way for the Blackboard component. So I advise you to try to do the exercise to prove things also for the Blackboard component. Okay, so let's do it gently. So this you will not you will easily discover. I recall that. Let me remind you that that epsilon t is square root epsilon e to the it over epsilon. So you will probably not be surprised if I tell you that this is 2 square root epsilon absolute value of sine t minus s divided by 2 epsilon. Okay, that I guess you will buy easily. And now I will use a very simple thing, a very simple trick, which is also useful for the proof of this general result, which is the following. So first of all, you see that this here is always less than 1, but it's also always less than the absolute value of t minus s divided by 2. The sinus x is always smaller than x in absolute value. Okay, so I get that this is less than 2 square root epsilon min of t minus s divided by 2 epsilon in absolute value and 1. Okay, that's fair enough. And then I use a further trick, which is then this is going to be less than 2 square root epsilon, and then I can. What I will do, let me just state it in general. Min of PQ, I imagine these are positive numbers. This is less than P to the alpha Q to the 1 minus alpha for alpha in 0, 1. Okay, this is well. No, well, I have to say I'm impressed because, of course, we all agree that this is trivial. This one, well, this is simple. This inequality here is simple, but you see that we can make something useful out of it. Here, I guess that I get that this is less than t minus s divided by 2 epsilon to the alpha. The 1 to the 1 minus alpha is going to be 1. So that's fine. Okay. So now this means that you see immediately if I take alpha equals 1/2, I get that the norm of z epsilon 1/2. Well, you see, if I take alpha here, the exponents are made in such a way that things go nicely for the epsilon. It disappears from the game. And here I divide by t minus s to the 1/2, etc. So t minus s goes away. So this is less than square root of 2 if I do the things correctly. So this is strictly less than infinity as far as I know. So we are in the position that this applies here. You see. And if I take alpha strictly less than 1/2, I guess that z epsilon alpha is going to be less than. So if I do it correctly, here again this is going to disappear, and so what I get is 2 to the 1 minus alpha epsilon to the 1/2 minus alpha, and because alpha, so this goes to 0. Okay, and then we have simple convergence. So simple convergence. And I also have modulus of z epsilon sup. This is close to 0. Sup of uniform convergence. So I've checked the hypothesis of the theorem. This in fact was in the hypothesis. So maybe I should call it beta this time. This is beta. This was in the conclusions, but I showed that the hypotheses were valid. I showed also that the conclusions of the theorem were valid. And then here also this was an hypothesis that I checked, and I check also the conclusion. Okay, so this maybe it's not in the best order we could imagine, but indeed this is just telling us that everything is working fine.
What is alpha less than the conclusion of your?
If alpha is less than 1/2, this goes to 0 when epsilon goes to 0. So that means that this path is converging to 0 in the alpha Euler topology.
It is a kind of. C'est bêta, ouais, non, c'est bleu.
So for every alpha, I showed the bound for beta equals 1/2 here, and I showed that in fact I have convergence in the alpha Euler topology for every alpha in 0 beta, which is exactly what this is saying.
But in the lemma, there is no convergence for in the beta Euler topology.
No, and in fact it's well. In fact, it's not the case. I mean, okay. So that's a good remark. Indeed, in fact, this example is even optimal because it's not true that there is convergence in the beta topology, in the 1/2 topology, because the maximum, the sup of, you see, that's a good point. In fact. So 2 square root epsilon times t minus epsilon divided by epsilon in absolute value to epsilon divided by t minus s to the 1/2. You see that this is well, there is scaling, so it's also the sup over let's say theta belonging to R basically of well, there are factors of 2, whatever. So okay, that's not important. 2 square root of x. I'm sorry. I want to write it down properly, 2 square root of theta and theta, I guess. And this one is this is non-zero. So we don't have convergence in the one after. It's optimal in that sense. You don't get better. So this means that this little lemma, which is essentially the proof, is not much harder than doing the computation we did there. But it even gives an example where this little lemma is optimally satisfied. Okay, so here is the teaser. And it's you can start the exercise if you want, but the little teaser. We are going to next time we will start by the following. We will have the differential equation dw epsilon is equal to w. If you write it correctly, w bar epsilon z epsilon. So this is going to be interpreted as an ordinary differential equation because these guys are smooth. So this will be this is to be thought as w dot epsilon is equal to w bar epsilon z dot epsilon, and with the initial condition that w epsilon at time equals 0 is equal to 1, we are going to solve it and see what happens in the limit epsilon goes to 0. So it turns out that this can be solved exactly, not too difficult. It's a harmonic oscillator essentially in these guys. It's a bit hidden, but it's an harmonic oscillator. And that's what we are going to do to start with next time. Thank you very much. They've been very generous because I've stopped at the time I should stop and not taking into account the minutes I wasted because some people were not able to switch on the microphone correctly. Just joking.
Yes. So it's question time, and no, not a question. Do you have any questions? Okay, please.
Just this example kind of a bit reminds me of this exponential of I times something divided by a small number. It's a bit like, I don't know, an action divided by h bar in quantum mechanics or something.
Yes. Okay.
Is there anything you can say with this? If I take a classical, because it feels like if I take a classical limit, I have something that classically is a path that is 0, but it still has something that you cannot get rid of. And I don't know if there are cases where you can use rough path.
That's a good question. I agree with you that it looks like, well, one of the differences is that usually if you look at mechanics, you have a stationary point in your action. And this is not the case in that example because there is no way. It's just t, so it doesn't have minimum or maximum. That's a good question. I mean, maybe rough path in infinite dimensions could say also. In fact, I do not know much of the literature, but the relation between rough path theory and the semi-classical expansion is something I'm not aware of. I mean, but okay. The idea is looks nice, but I don't know.
More questions, maybe from the virtual room. We give you 20 seconds.
It's not raising. Yeah.
So the fact that there is nothing going on in one dimension and higher, so okay, yeah, it has to do with you are playing with vector flows, etc. Some things which
Well, the point is that
you are playing with rotational here.
yes, that's correct. That's correct. Okay, definitely. The stupid technical point I had is that if you look at the exact the pieces which are exact differentials Of course, if the path is converging pointwise, the exact differentials are going to be nice as well. They will converge pointwise as well. I mean, so you can just take the limit very naively. The only opportunity you have to have a non-trivial limit is when there is no exact differential. So you have to really compute the integral of y dx. And so in one dimension, this cannot happen.
You have non-full differential.
Yes, yeah, you have differential, not tautology. Well, there is a theory for that, but yes, these are not exact differentials in a trivial sense. Of course, they are in some sense they are trivial differentials because I was able to compute the integral explicitly, but they are not trivial in the abstract way. But indeed, you're right, and in fact, all the examples I will show you, in fact, all have to of half path have to do with the fact that some area is going to be accumulated by some process. This is the zeroth order example, but the waltz with Brownian motion is going to be another example of it.
So your point example in the first diagram, so
Yeah.
it's very closely related to that.
Yes, it's yes, I agree. But as you maybe you asked the question, there were square. Well, we are not really looking at square root of x prime plus y prime. Like we are not really computing length in these exercises, but we could probably adapt the techniques. I mean, but that's not what we do. But it's closely related, definitely. The 20 seconds are over, so.
Yeah, so I think we can stop here. So see you next Friday.